share screen. I can close this. And where's that PowerPoint? Well, for those of you that did try the assignment, that's a good thing. And so basically, okay, annotate. Okay. So basically, we're talking about, a double angle bearing type connection. Okay, so this was the size of the beam here, 530 by 109, and of course, the type of steel, like I said, these were the Canadian mills that used to produce this type of steel, and now it's the A922, the Americans, but pretty much the same. The beam is simply supported and has a span of 3 meters. Okay, so the reason why we need to know the span is that based on the span, and if we go to the load tables, we'll be able to determine what is the maximum load that this beam can carry. The angles are to be welded to the beam and bolted to the supporting member. Okay, and like I said, that's one option. Okay, and I don't know if you guys realize the like the advantage of welding to the beam and bolting it to the supporting member. Here, I didn't tell you what the supporting member is, so you don't have to worry about the thickness of the supporting member. Make sure it's okay. I just want you to realize that typically the members are welded to the supporting member and bolted to the beam. Typically, they do that because by doing it that way, you're taking advantage of the double shear in the bolts, and you only need to put 3 bolts as opposed to putting 6 bolts for this type of connection. So that's the slight advantage of always typically doing it the other way. But then, of course, you got to coop the beam, this and that. There's other, but anyway, so give or take. But like I said, typically you would bolt to the beam and weld to your supporting member. The threads or the bolt are to be excluded, okay? And guys, if you are designing with the threads excluded, specify in your specs, okay? All threads to be excluded from, okay, from the shear planes, okay? So you should specify that so the guy knows that he's gonna have to make sure that he orders the right size bolt so that when the bolt goes through the connection, the last shear plane is still on the shank and not in the threaded connection. These are things that the steel detailer will make sure of. And of course, and then at the same time, if he's an honest erector, he'll also make sure he's got the right bolts, okay? And ultimately, of course, that should be inspected to make sure that everybody's doing it correctly. And now show your final results on a sketch. I always do this because it helps you. If you know how to sketch something, it helps you to read drawings a little bit easier. And that's why I always, and then of course, it also helps you developing your sketch capacities. And that's why I always ask you to show your, and as a matter of fact, in real life, nobody cares about your calculations. Nobody cares about the number of shear planes. Nobody cares about anything. All they want to see is, what do you want me to build for you? And that's basically, and remember guys, there's a simple rule somebody told me way back when: if it can't be sketched, it cannot be built. So that's another reason why it's good to have a sketch. If you can't sketch it, most likely you can build it, okay? So keep that in mind. Now, of course, we're gonna start here, and we said it was a W5.109. Okay, I just want to keep in mind what the designation was. So here we have 109, and I come here because all I want to have is the thickness of the web, okay, from this table. In other words, the W shapes. So I know that in this case, the web has a thickness of 11.6 millimeters. So that's what I want to get from there. Now, after that, I want to be able to determine what would be the maximum load that this beam can carry. And so, for example, if I'm looking at a drawing and the architect, or not the architect, the structural engineer did not put the shear forces for the connections, then I would design it for the maximum load, okay? And here we have a W530, and of course, these are the different sizes, and therefore I go for the span of 3 meters, and I see that the total uniformly distributed load, okay? So the total uniformly distributed load for laterally supported beams, okay? And of course, here is the maximum load. So in other words, this was based on the fact that they calculated based on the maximum bending capacity, MR, what would be the WF, and then from the WF, they calculated what would be the total maximum load on the beam. Because hopefully the beam will fail in bending before your connection fails, and that's why. Okay, so here we have 2,340 kilonewtons. And of course, if you consider that you know, the beam is, you know, like this is the beam here. It's being supported there, and you take it to be a uniformly distributed load acting all the way across. You know that half will go that way and half will go that way. So, and therefore you can take the shear force here will be half the value in the table. So if ever, okay, and last viewed. So here we have a total factor load of 2,340 kilonewtons, and of course this is the whole, and as I just explained, the shear force on one side of the beam would be half that load, 1,170 kilonewtons. Now that I've got the load that or the force that I need to resist, of course, I go to the tables, okay? And I said it was going to be bolted or welded to the beam, and I want you to use a 76. I specify the size because I want, you know, you guys to narrow in on what I'm looking for as a solution. But remember, if you're doing this on your own, you choose what you want W to be, okay? So I will go to 1,170. So here we go. So what I did here is I simply, okay, so I'm at, so I am welding. Now keep in mind, when you're looking at this table, okay, this diagram is to show you how you are connecting the angles to either the supported member or the supporting member. So this is when it's being connected to the web. This is when it's being connected to the supporting members up here. So that's why by this diagram, you know that am I here or am I here? That's okay. And therefore, I told you that it's going to be welded to the beam and connected and bolted to the supporting member. And of course, like I said, the advantage is that you don't have to coop this, okay? You can leave it the way it is. The disadvantage is, of course, that you're using more bolts to do the connection. Now, so I come down and I look for a VR greater than 11, whatever it was, 11 something, and therefore here I have a VR of 1250, perfect. And I know that in order for that to develop that resistance, I need to provide a weld on both angles, of course. You know, like, and here you see the pointing, and therefore this would be an 8mm weld in there, okay? And at the same time, I would go down to the table to see what is the minimum required web thickness of the supported beam, and I need 12.1 millimeters, okay? So that's the two things I get from here. I get both the minimum web thickness and what the shear force would be. And of course, I check to make sure that I had a, what was it, 530, so therefore the beam size is perfect. And of course, I need to remember that the length of my connecting angles is 390, so this way when I go to the other side of the table, I'm always looking at the same length to be able to determine the number of bolts. So here I have for a W76, D is 8mm, VR is 1250, and VF is 17. Now, this is where, you know, like I showed you in the lecture that you always prorate the thickness required, okay, to see what is the actual thickness that you need. And in this case here, if you wouldn't do that, then you'd say, well, I have a problem because apparently I need a thickness of 12.1 and I only have 11.3. And if you don't prorate what is actually, okay, so here if you don't prorate what's required over what's provided, okay, you end up saying that, well, I need 12.1, I only have 11.6, therefore I have a problem. No, you don't have a problem, because when you prorate the actual thickness you need in order to develop a force of 1170, you only need 11.3 millimeters. And since you have 11.6 millimeters, your web thickness is strong enough for a force of 1,170, okay? And I like to do this all the time. So even like I know, for example, sometimes it looks redundant when, for example, I need a thickness of 7 point something, and I know already I have 8.4. In a sense, it seems pretty redundant, but it's just to remember that you are allowed, or you should always see what is the actual thickness you need in order to develop the force that you have in the tables. And this is a very good example that if you don't do this, then you say, oh, I got a problem. You would have chosen something else. Okay, so now now I'll worry about the size of the angles once I've gone over and chosen. Okay, so now that I have the bolted side of the connection, okay, so I'm going to go So basically on the bolted side of the connection, well, what's happening is I know that my bolt size are 12 millimeters. And on top of that, I know that I have the threads are excluded here. I have, okay. And the other thing is that remember that when we were on this side of the table, we were at an angle of 390, okay. And therefore I have to stay in the same line because I cannot have one side 390 and the other side. I mean, you can if you know, but you should try to stay with the same length of angles on both sides. And you know, I mean, under very special circumstances, you can probably change this, but I wouldn't recommend you do it. And then of course I'm looking for M20 bolts, so therefore I need to go over 1170, and therefore I have 1250 here, and this gives me 5 bolts, okay. And at the same time, so I'm not worried about the thickness of the web because I'm not connecting the web, I'm actually connecting the size of the framing angles. And here it tells me that the minimum required thickness of the framing angles is 11 millimeters, okay. So I should be using at least 11 millimeters thick framing angles so that I can make sure that the bearing here is sufficient. That's why and of course, all the other requirements. So here we go. So 5 bolts, threads excluded. We have a VR value of 1250 or VF value of 1175. Fantastic. Minimum 11 millimeters. Now, I'm not going to prorate this because I'm going to go look at what we have in terms of angles. So 76 by 76, these are the standard thicknesses, okay? Guys, these basically what this is, these are imperial sizes that have been converted to metric, okay? So this is 3/16, this is 1/4 of an inch, this is 5/16, this is 3/8 of an inch, and so on and so on, okay? So here I have a 76 by 76 by 11. So therefore I know I have one here, so that's what I'm going to be providing. So I just come to these tables to make sure I pick a thickness that is actually going to be produced by the mills. Okay, so a 3-inch by 3-inch by 11/16, 11 millimeter thickness is good. So, and therefore my framing angle is 76 by 76 by 11. Now, the last thing I'm going to do to make sure I don't run into a problem, I'm going to check my weld. Okay, I know that according to good practice, that in order for me to be able to weld an angle, and because of the fillet here that the angle has, that my weld size here should not be more than 75 or 0.75% of my T here, and that should be my maximum D there, because to make sure I don't encroach onto that fillet, and therefore I need 8.2 millimeters. That would be the maximum weld. And from our previous, we realized that we had, oops, sorry. Okay, so therefore 8.25, and I know that my D is 8 millimeters, so I know my weld size is okay. Fair enough. I should have written it down here, because if I go back, you'll see that we chose an 8 millimeter weld, and I can go right up to 8.2 millimeters, so I'm okay. So once that's done, basically, okay, you basically show, you know, that you're welding to the web and so on. This is a standard dimension here. Okay, in other words, you always leave 10 millimeters. Okay, so for example, you always leave a 10 millimeter gap between where it's going to be fastened to the supporting member to where the end of the beam is. Okay, and that's where the shop drawings come in. Okay, when you make shop drawings, the guy that does the shop drawings, he'll look at if the columns are like this. If the columns are like this, and he's going to be putting the angles on the beam here to support the beam, and this and that and that, okay? So that's where the shop angles come in. For example, what you see on the structural drawing is, of course, the distance, the span here, or the distance between the axes. And the guy that's doing the shop drawing, well, he'll calculate the size of the column, take half there, and then remove 10 millimeters. And on his shop drawing, he's going to be specifying that this beam has to be exactly this length, okay? And that the guy that does the shop drawing, he does all of that, and then he details everything. So he also, okay, so this is where, and this becomes a standard, you know, 3/8 of an inch in the old days, 10 millimeters these days is what you leave, so that when they drop the, you know, like it gives them, you know, it gives them a little bit of Flexibility during the erection of the structure for the erectors. And of course, you should be specifying. Now, remember, the welding detail is that you always show, if you put it on the underside, then it's referring to the side that you're pointing on. If, for example, I wanted to show the other side, well, then I would put it above, okay? And here, of course, I'm just going to show that, well, this was the size of the angle here. But for example, if I know that this is a 76 by 76, well, the guy's going to be welding here by 76, okay? And of course, you always put the steel that you're using. And like I said, today you might be able to find many angles made with 350W. I think they started to produce that. Not 350 anymore. I'm talking about the Americans that started producing it with the A9225 for the steel angles. And of course, don't forget that if you look at the table, it says that the electrodes are supposed to be E490, okay? E49XX, which means that it has an XU value of 490 megapascals. Okay, the XX, like I said, is the specification of the electrode itself, and the weld is going to worry about that. And of course, here you don't worry about the gap. Why don't you worry about the gap here? Because you're actually welding to the web. If I was bolting to the web, then I would have to specify at least 2 to 3 millimeters wider the gap here, so that when they drop in the beam, and not less than 2, not more than 3, the gap here plus my web thickness, if I would be bolting to the thing and welding to the supporting member. And of course, you show the end distances and the pitch between each one, and of course the length of your angle, and of course the gauge between the bolt size. Now, I don't show it here, but one of the things that you have to take into consideration is that, for example, if this is sitting on a column, okay, you got to make sure that your column is, if this has, you have to make sure the column is wide enough, and so on and so on. So there's other little things that should be taken into consideration. But like I said, this is basically the steel detailer, okay? And I just want to say one thing. If, for example, I have a column here, okay, and I'm going to be welding to the column. I'm going to be welding to the column, okay? I'm going to be welding to the column. And all of a sudden, I say 76 by 76, my angle, and then when I start working it all out here, I don't have the room. Well, you're not going to use a 76 by 76. You can use a 52 by 76, make it smaller. You understand? Whatever you need in order to make sure you have enough, okay? Because if you look, I want to show you something. If you look at the, let me show you something here. Clear all drawing. Okay. I want you to realize one thing in this table here. Let me go back to, where was this? Here, this one here. Framing angles. Okay, no, not here. I want to go back, last viewed. Oh yeah, this one here, okay. I want you to realize something. Oh, not this one, the very first one. I apologize, last viewed. Okay. I want you to realize something here, okay? Like here, I don't know if you realize this, but if you look here, okay, this is a 76 and this is an 89, right? And if you look down here, okay, this is the resistance whether I'm using a 76, and this is the resistance whether I'm using an 89. What does that tell you? Does anybody have any idea what that, like, for example, here I got 1450, here I got 1450. So all of a sudden, whether I'm using an 89 or a 76, the resistance I get is the same. If you look here, the resistance are the same, okay? It's only when I get into some very small angles that the resistance changes slightly. I don't know if you see this, okay? But after a while, the resistance, whether I'm using a 76 here or an 89, I have the same resistance in the table. Why is that? Did anybody can venture a guess, or has nobody ever really noticed that it made a big difference? Does anybody want to venture a guess?
Is it because of the same number of bolts and weld lengths?
Weld lengths. Here we're not talking bolts, weld lengths. Okay,
Ah,
so in other words, here the weld length is the same, the return is the same. So all of a sudden you're going to get the same resistance whether I'm using a 76 or an 89. Exactly. Okay. Now the only time that it changes slightly is that when the angles get smaller. Okay, what happens is that because these angles get, like they're supposed to be somewhat flexible and they tend to, bend out, and therefore it can create some additional forces. So if ever you need, for example, if ever you need to go down to, you want to weld with a 52 here, okay? If you want to weld with a 52, well, you know that if that angle here happens to be, for example, it happens to be 390 millimeters long, well, whether this length here is 52, whether it's 76 or 89, right? They're all going to have the same resistance. So you can change the leg, for example, if all of a sudden on my column, I cannot put an 89 or a 76, this happens to only be 104 millimeters, well, then you know that you're allowed to make it smaller, because what's really giving you the resistance is the weld, not the size of the angle. I want you to keep that in mind, because I think in the project you're going to have a problem if you stick to these standard sizes. You're going to have to modify the size of your angles in order for the double angle connection to fit on the columns that we chose, especially on the exterior perimeter. You understand? So that's all I'm trying to make you understand, is that it is, in this case here, it is the size of the weld that, okay, gives you the resistance, and not the size of the angle. And especially, like I said, when they're very small, because when it's very small, these angles tend to flex out a bit. I found a nice drawing showing you how these things flex out a bit because of the
so
rotation. But
so for
yes.
sorry, so for the project, we're gonna have to take a longer length, is what you're saying?
No,
For
what I'm saying is that if you happen to take, if you need, if all of a sudden a 76 by 76, which is the smallest one, doesn't fit on your column, you're going to have to make, you have to take smaller legs, or you're going to have to cut them.
okay.
That's what I'm saying. So, but what I'm saying is that when you're looking at the resistance, okay, like for example, if for example here you look at 89 gives me 135, this gives me 140. So as the leg gets smaller, that means the resistance goes high. So even if I take this value for the resistance, I'll still be okay. Yeah, I don't know if I've lost you all on that, but what I'm trying to make you understand is that you can still use these tables, even though this is not one of these standard widths here, 76 or 89. You can go down to 52 if you want. You understand? So that's all I'm saying. So keep that in mind. And then here, the only reason why here it changes slightly is, of course, like I have 76. So here would change slightly because this is a little bit longer than this one. So therefore the resistance up here would be slightly bigger than the ones down here. That's because this is 76. I have a little bit more here, a little bit more there. And that's why I would have a slightly higher value. Okay. But in reality, what's really giving most of this resistance is this weld right here. You understand? It's not that little bit of addition there. So
So if I understand that, it, like even if we go with the width, a lower width, it would still work because we're depending on the
on the weld, you
yeah.
understand? It's the weld. So for example, look, right now here they're saying 89. Okay, 89 gives me 135. Let's just say, right? 70, like let's say you need a very small angle. Okay, and here 76 gives you 146, right? What happens if I happen to need to cut my thing down to 52? In other words, I can only have a 52 millimeter, because I think the next standard size is 2 inches, which is 52, I believe. Okay. Or
It's
is
gonna
it?
go a little bit higher, which is good.
No, what I'm just saying, like the standard angles, unless you understand, like you either use a standard angle or you ask the guy to cut the angle. You understand? To cut the leg to fit in your geometry. Because so what I'm saying here is that if all of a sudden I'm using 52 here, but I'm using the same length here of, okay, the length here is going to be 150, right? 150 is the length here. And this happens to be 52. And if I'm welding here like this, can I say that the VR of the leg is still going to be 146? Yes, because we have the same amount of welding as we would have for a 76. And it seems that as this leg gets a little bit smaller, the force only goes up. So I can rely on this to give me the value of, or if I don't want to rely on this totally, I can actually do the calculation what the VR value is here of this weld and make sure it's greater than my VF value. But I can still use the tables to give me a very good idea if I have sufficient resistance. I don't, maybe I've lost everybody. I'm not sure, but
This does not work with the web framing. Like I can see slightly difference in the value, or
this would,
would it,
like
is
what
it
I'm
also
saying.
considered for the web framing?
Well, I'm sorry, Norman. Can you repeat that? Because you were coming in and out. It sounded like you were.
Okay. Could we consider the same for the web framing or only for the outstanding leg? Because in the web framing, there's like a slightly difference in the values
You
between
know,
the
no. But in the project, I'm going to tell you to all your double angle connections for your project. You're going to be bolting here and welding to the supporting member. So we won't even be here. You understand? So for the project, you're going to be using bolted. You're going to be bolting to the web of your beam. Okay. So that's what you're going to have. And then you're going to be welding to your supporting member. So you're going to be welding to the columns. Okay. So what I'm saying is that, well, we'll talk about the project and then I'll go over this again. So, and okay, but I want you to keep that in mind that you can still use these tables to determine whether the size of weld would be sufficient to support your beam. That's all I'm saying. You know, people say, well, sir, we don't have a 52 millimeter angle in the tables. You know, you don't, but you can have the resistance of a 76. And if you're using 52, it would still give you, I can guarantee it will be the same value. Okay. And especially, for example, if you come to the table, you get 146 here as your VR and your actual VF happens to be maybe 81. What do you care? Wow. You have ample resistance. So all I'm saying is that I want you to keep in mind that when you're welding to your supporting member, okay, what's important is the length of the weld here that gives you the resistance. It's not the width of your of the angle. Here, the width of the angle has a bearing on the resistance because as this gets longer, you get a little bit more weld. But for this weld configuration only, you see that after a while, I don't know if you notice this, but after a while, it makes absolutely no difference. Okay, it's only like for the very small ones here that there's a slight difference in resistance, but then after that, they're all exactly the same value. This value is exactly the same as that one. That one's exactly the same as that one. So after, like, as the angles get longer, these are the ones that are really going to be giving you all the major resistances, the length, and that little return here is going to be so minor in what it contributes that it's going to become insignificant. Okay. And what I'm saying here is that you can still use the table to determine what your VR value is, regardless of the width of the leg that you're welding to your supporting member. For example, if my column only has 104 millimeters wide, that's the width of the flange. How am I ever going to be putting a 76 by 76 back to back here as my supporting angles? Where am I going to weld this? My angles are going to be coming way out, right out here. If I keep this, my angles are going to come right out here like this. How am I ever going to be able to weld here? Okay.
Yeah, I see.
You if you want, you can weld on the back side here of that. You know, you can create a weld there and make a return, but that would be like, you don't have to do that. You can actually either cut your angles or use smaller angles, you know, use unequal legs, you understand, use a smaller angle. This one you should still keep to be, you know, the same size so you can put your bolts here, but here you can make it smaller and then you can make sure that you can weld there. And then after that, you can still rely on this table here to get your VR value because it is the length of the weld that gives you your VR value, not the width of the leg, especially as the welds get longer. That's all I'm saying. Okay. You know, like what I'm saying is that we'll do maybe one example together, but if you guys aren't clear on this, we can clarify that. But I want you to keep that in mind. Okay. And then ultimately, you know, like I said, if you want, you can actually, excuse me. Okay, you can actually calculate the VR there and make sure you have sufficient one. Okay, so that's, I think that's it. Last viewed. Okay, so that's pretty much it. Yeah, and so everybody understands, like, okay, so the sketch to me is, you know, like I said, 5 M20 bolts. You specify the strength of your bolts, you know, and make sure your sketch has all the specifications of all the materials that you use, because all your whole design was based on the resistance of that material, and you want to make sure that the guy is going to be supplying what you use in your design. And I think that's it. Yeah. So everybody's clear on the double angle connections. I'm going to end show. And as a matter of fact, okay, what I'm going to do right now is I'm going to talk about the lab. Okay, so let me talk about, okay, I don't even have to do this, but here. Now, the last thing that you guys are going to have to be responsible for, I don't know, there you go, okay, is of course, okay, now here I made some corrections to this drawing, okay, so I want you guys to don't use this drawing here, use the corrections. Now, last week we talked about, I mean, we did this connection already, okay, the only thing is that I want you to, this is the number of the detail. In other words, it's going to be on sheet number 3 and become detail number 2, okay? Here, I want you, when you do the double angle connection for this one here, that's going to be detail number 1 on sheet number 3. And if you look at the template, I've already named these properly for you. Okay, so make sure you put them in the right little spot. And then I want you to put, this will become like, here I want you to design the double angle connection for this beam here. And it's going to become detail number 3 on sheet number 3. And this, of course, is the little double angle connection of the perimeter beam. This will become detail number 4 on sheet number 3. Okay, so I hope everybody's clear on that. Now, I don't know if you guys notice this, but you know, every year I get the same mistake. So in order for you guys to minimize, okay, what the mistake that they made here, they forgot to show where the vertical bracing was on the plan view. Although we have it in the elevations, it's good also to show it in a plan view. And how do you show that on a drawing? Well, you basically, you show a, you know, you show a dotted line like this, okay? And then you show a dimension of 0 inches. In other words, that means that this vertical bracing is right underneath that beam. And then you just put here, you put a leader and you put vertical, or you put, you know, vertical bracing. And you should always show where your vertical bracing is on your plan view. So this is one of the mistakes she had. And of course I penalized her for it. She forgot to do it. And other than that, everything else, like yes.
You were saying 0. What inches?
Well, in other words, when you, like if you go back to your first drawing you did in drawings 2 and go look at that drawing, and you'll know how to dimension the vertical braces, because that's where we do that in drawings 2. Okay, so go to your first assignment in drawings 2 and look at how it's dimensioned in drawings 2, and that's where you're going to see how it's done here on this drawing here. How's that? I don't know if you kept those assignments, but that's where it would be shown. And basically what you do is, like, you always show, like, you show like a dashed line, and all you're doing is you're showing a dimension between there and there, and you're going to be putting 0 inches. In other words, what that means is that this line is not really offset from that line. This line is literally underneath that beam. In other words, the beam is here and the brace is here. That's what that means. You understand? But in plan view, you can't put one line on top of the other because you won't see it. So the way you show it, you show where the line is, where the location is, and in terms of where it is actually located in plan view, you're telling everybody that it's underneath this line here by putting a 0 inch here. And that's how you dimension that. All I'm saying is that here she forgot to show where there's no vertical bracing there, but there's here, 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 and here. So she forgot that, and of course I penalized her for it. Okay, so that's it. So that now, of course, where do you get the value of VF for this? You get that from ADA. You get the VF from ADA for here. You get the VF from ADA there, and you get the VF from ADA there. If you did all these 3 beams, and that's where you get your VF value. And of course, then you design your connection. So, and like I said, Here, what you have to worry about in this one here, when you do the detail, for example, you know that you're putting your connection, you're putting 2 connections in here. So therefore keep in mind that this has to be double the thickness required because you're putting the bolts on both sides here. And at the same time, you have to make sure that here's my flange, and whatever angles I'm putting in there, okay? Because okay, now for these here, okay, for these here, right? So you got to make sure that you can actually go and weld in here and that you specify the right size angles so that it fits in between all of that, okay? So that's one thing you're gonna have to worry about. Or if you're gonna have, or if you guys want, I'm gonna give you the option. For these beams here, what you can do is you can be bolting here, but the bolts won't work because I don't think you'll have enough room, okay? So you're gonna have to weld and you can make sure that everything fits in between those 2 columns. And then on here, it's the other way around. You have to make sure that your 2 angles will fit on the width of that flange. So that's something that you're gonna have to work out and know what the size of that flange is, and then be able to calculate how long this leg has to be in order for that thing to work. And I'm gonna expect to see that on your details. And so that's it. The rest, like I said, okay, so this, like, keep in mind here the numbers, because that's, I'm gonna expect everybody to have the same numbers. Matter of fact, let me just make sure of something. Hold on a second. I think I opened up my AutoCAD here. Does everybody see the AutoCAD drawing on the screen now?
Yeah.
Okay, so there you go. See, like, this is, now I'm gonna pan out, okay? Now guys, look. Okay, I've already started you off very nicely so that you guys know where to go. So I've even made this very easy for you. Okay, so this is just copy, 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 blah, blah, blah. And when you do the details, right, believe it or not, okay, you're gonna still work on a one-to-one detail here, okay? So for example, if you need to draw 600 millimeters, well, you're gonna say 600, okay? And that's going to be a 600 millimeter line. If that's going to be 400, then you put 400 and so on. So you still draw one-to-one, but you're actually drawing at a smaller scale. The only difference is that when you come to dimension, okay, remember I created another dimension style for you, and that's the 1 to 10 scale. So you pick that one, you set it, you put set as current, you pick that one and you set as current, and then when you come to dimension, for example, linear, from there to there, it's already set properly for the scale. If you don't change the dimension style here, and you still use a standard one for the overall scale of 1 to 200, if you use this one, this is what's going to happen. Okay, if you use this one and I come to dimension linear here, from there to there, I didn't change it. I didn't set as current. Sorry. There, standard set as current. Okay, and if you don't happen to change the dimension style, when you're going to come to dimension, this is what's going to happen. You're going to go from there to there, and this is what you're going to see. So that doesn't work. Okay, so I've adjusted your dimension style so everything works perfectly. So just go ahead and change your dimension style, and then when you're ready to plot this drawing, you just have to specify the right scale, 1 in 10 instead of 1 in 200. And on the sheet I told you, it's going to work perfectly. Okay, and that's how I like to work with AutoCAD. I like to make sure that my sheets will eventually, that my drawings will eventually fit on my sheets at the scale I'm drawing at. And I go ahead and instead of doing viewports and this and that, I don't have to do viewports. All I got to do is change my dimension style, or adjust I don't even have to change it. I just have to adjust my dimension style to this scale, and it's done. And if you guys want to see how it's done, go look at the dimension style under standard, go look at the different variables and see how I adjusted it. So just keep that in mind. And that's it. So this is where you do all your drawings. And this, if you notice here, I've already named them for you: connection, Gerber girder, exterior column. That's why I want you to make that detail number 1, detail number 2, detail number 3, detail number 4. Okay. So this way, when you're drawing it, you're going to be drawing it here. And then of course, here you're going to be putting your baseboards, vertical connection to the brace, base plate, and this is where you do. I've already given you where I want to see. So therefore, when you're going to go in your drawing, and you're going to be locating where this detail is. This is what you're going to be using. 1 of 4 is for the vertical brace at the top. 2 of 4 is for the base plate. 3 of 4 is for the vertical brace at the bottom, and so on and so on. So make sure you use these numbers here and indicate those properly, either on the elevation or on the plan view. And that's where I want you to, okay. So I think the base plates, you don't have to indicate them anywhere. Oh yeah, interior columns, you don't have to indicate these because these are typical, so therefore you don't have to show where they're located. But this, you're gonna have to show on the elevation where these connections are, and you're gonna have to draw them here. And that's it. So you're pretty well done. Now the rest is up to you to have it done and, you know, hand it in on time. And that's pretty it. So what I'm going to be doing, of course, I'm going to just be sending you the that sheet that I gave at the very beginning of the semester. I'm going to put that on the assignment sheet, and I'm going to have a cutoff time. And I think I'm going to give you, like, for the wood, you're going to have until 6 o'clock on the last class, because that's when the thing ends. Okay, for the steel, you're going to have until 10 o'clock when the last class ends in week 15. It's going to be indicated. And I expect you to submit your drawing, your design brief through the assignment. And of course, I will not be accepting any late assignments. Any assignment that's not in there, okay, don't wait till the last minute to do it, because you'll lose 50% of your mark. That means you'll probably have failed, you'll have failed the project. So don't do yourself a big favor. Don't wait until the very last day to submit it, because if it's late, you'll lose. I don't care if it's 1 minute late, you will be losing 50% of your assignment, of your project right there and then. Okay. So I'm going to be posting that sometime this week. Okay. As a matter of fact, I might even be posting it today. And this way, all you're going to see is and then of course, you're going to be submitting me. I'm going to be writing it on the assignment that I expect you to submit me all your PDF information in the assignment, and then by Leah afterwards. I don't care when you're going to be doing it by Leah, but by Leah, I want you to send me all your drawing files, whether you did it with AutoCAD or whether you did it with Rivet. I want you to send me your drawing files through Mayo. Okay. And if you don't send me your drawing files through Mayo, you will be penalized. Okay. So the drawing files, I want you to send, I'll be explaining that, but your PDF has to have the same order. And at the very end, I want to see all your drawings in PDF in your design brief. So that's like, cause I'm going to be correcting your drawing, because I'm going to be correcting the design brief and the drawing simultaneously. And that's going to be and then I'm just going to be verifying your AutoCAD drawings individually, because, you know, to make sure that everybody did his own work. And that's
Sir,
it.
I have a question.
Yes.
Could you go back on the other drawing, the S1 drawing that you showed just before?
Sure. Can I? Okay. So you want me to go back to the S1 drawing? Okay. So do you see it on the screen now?
Yeah.
Okay.
If
Go
you
ahead.
zoom into, I don't know, section D4, the grid line there.
D4. Hold on a second. You're talking about D4 here. Okay. Yeah.
Yeah, there's little numbers, like sometimes it says minus 500. Is that the elevation or is that the spacing between the
I've explained this when I explained the drawings. So go back to the
okay.
video and look at the video.
Okay, perfect.
Okay. Like I've explained this. So go back to the video of lab number 5 and listen to the video.
Okay.
Okay.
Thank you.
So that's all I'm saying. Like from here on in, like guys, you better ask me questions during the lab period. You send me a Maya, I'm going to say wait until the lab period to answer the question. So I explained that on the video, what these numbers represent. And if you don't remember, I'm going to refer you to which lab you should go back to, which video you should be listening to. And I explain all of that, why we have these numbers here. Okay. So that's it. And I got nothing else to say for today, guys. Pretty much that finalizes the project for steel. And like I said, I hope you guys have moved your drawings along a bit, and that I can hopefully everything get finished and finalized. So I'm going to stop sharing, and I'm going to now open the rest of the time to questions. If there's no questions, then you guys, I strongly suggest you go and work on your project or whatever else you need to do.
Sir,
Yes.
Are you gonna make the project submittal like assignment thing only like this week, next week, or
I'll probably do it. I'll probably do it today.
okay, cool.
You
Perfect.
understand? Like I'm gonna do it today, and I'm just
And
like
you,
I said.
okay, and you also said you want to see all drawings in our like Word PDF file brief.
Well, look, I'll open up. I'm gonna open up. Hold on a second. I'm gonna open up the what I sent you. Hold on a second. This way we're all on the same page, and I don't want to hear any. You understand? Like, hold on a second. Desktop, Dawson. I'm gonna open up the steel one. Where's the steel structures? Where do I have the design brief? Where's my design brief? Did I have it here or do I? Oh yeah, steel design. Okay. Okay, so hold on, I'm going to share this with you guys, and therefore close this, close that, share screen. Okay, so here was, okay, this is what I sent you at the very beginning. And
Yeah.
okay, and therefore, look, it says it here. So this is the order I expect to see all your calculation.
Yeah, of course, yeah.
And then here I say, at the end, you're going to show me, you're going to make a, you know, when you plot your drawing, you're going to be plotting as a PDF, and you're going to be including this in your design brief, your S1, your S2, S3, and S4.
Okay.
But then I don't want you to send me, all I want to see in Leah is your PDF file, okay? And then in Leah, I want you to send me your drawing, your drawing files.
Oh, as a Maya. Okay, I see.
Through Maya, and
Okay,
and I'll write that in the description, that I expect you to have your drawing files through Maya, and in that assignment, I'll put that in the description to remind you to do that. You understand?
Okay, I see. Okay, perfect.
And then I'll remind you again the week before. You know what I mean?
All right. Yeah.
But, okay, but what I'm saying is that I'll probably all I'm going to be doing in the assignment, I'm going to be attaching this. So this is what the file you're going to have attached. I'm going to give it a title on the assignment. I'm going to call it project. Okay, so this way you can find it right away. I'm going to give it a different name and call it project. I'm going to be attaching this file, and in the description, I'm going to be putting the like to send me your drawing files. Whether, I don't care if you did it with AutoCAD or with Rivet, but I want you to have your drawing files. And of course, with Rivet, you only have to send me one file. Mind you, you only have to send me one file also for AutoCAD, because you're going to be doing everything on the same drawing, right? So you send me your AutoCAD file. And then, of course, you'll see the cutoff time. I'm going to specify what date and what time they have to be submitted. And as soon as you're done, guys, do yourself a favor. Just send it in. This way, it's one less thing you guys have to worry about, and you won't be pressured that you're gonna, all of a sudden miss the boat. And like I said, guys, come, I think the last Monday of the semester, come, 8:52, and you said, or I say, let's say the cutoff date time is going to be at 10 o'clock, and all of a sudden it's 9:52, and you say, oh, I got ample time to send the thing, and everything crashes, and then you send me a message, says, oh, my thing crashed and I couldn't send it. I'm going to say, well, not my problem. Because it's like, for example, I gave myself enough time to drive to the airport, my car broke down, and I couldn't get on the plane. Well, you missed the plane. That's not my problem. You haven't allowed for any contingency. Well, and that's how and I'm just trying to show you how it is in real life. Like, in other words, when something is due, okay? And if it doesn't get done on time, for example, I stress this in the spec class, like, you can spend days upon days about preparing your proposal, and you go to the city and you go there 1 minute late after the closure of the proposal, the period, they will not take your bid. So all that time is wasted. Okay.
Sir.
Yes.
There's well, for me, I didn't I have a bunch of Excel files, like for the exterior columns, Gerber girders and stuff. So do you want us to convert that in PDF and send it to you as well?
No,
Because,
like you take shots and you put it, like, I want to see one design brief.
okay.
In other words, like, I can show you some that I've seen so far. They're very well done. They take snapshots. Like, what I think the best thing to do, okay, is like like one person's like, I don't want to say who it is, but I love the way they're putting it together. Okay, and it's really nice. Like they're taking shots, they're converting it to PDF, they insert it into their Word document. It's all very nice. It all follows, like the Excel spreadsheet is there, the ADA is there, and then at the very end, once everything is done, I'm pretty sure the person's just going to have to save it as a PDF and then send me the PDF. But it's all going to be done. You understand? I don't know if you guys know what I'm talking about, but like for example, here, like in this PDF here, like for example, this PDF here, if this was a PDF and I only wanted this part here, well, I take a snapshot of this is all I want to show, and then I go stick it in my Word document. I'll adjust the size, and it's going to be there. And then when I'm ready to convert everything into a PDF, take my Word document, save it as a PDF, and it's all done. I mean, I can show you that, and I saw that I was a really nice way of using the software to be able to compile a very nice drawing. And the person that did that, I was very happy. You understand? Okay, so, and as a matter of fact, it was like I appreciated how that person was putting that thing together, and and I think the person knows what I'm talking about, but it was very well done. And anytime they had a question, they just send me their file and I'd be able to look at it, and it was easy to follow and it was easy to answer the question. So, so guys, use the tools, and like if I have to start scrambling across your PDF to look for things, like make sure it is very chronological. And like I said, don't try to save on a piece of paper. If I tell you that every section here, I even say it here on this, I believe I even say it here, okay, that, okay, I want you, okay, design briefs must have all the calculations for all the components listed below, okay, in the sequence, and in the sequence as outlined below, the headings 1 to 4 must be written at the top of each page, okay? So in other words, this should be 1 to, so in other words, once you do this, okay, and you're ready to do the Gerber design, start a new page. Start a new page. So this way I know that I don't have to like worry about, so I'm going to be looking at your headings, and the easier for me to follow your design brief, believe me, okay. Now this, we've done it in class. I expect you just to have it in your design brief. We've done this in class, you understand? So I expect you to have a snapshot, like take a, print this and have a snap and include that Excel spreadsheet for the design of the columns, because these are stuff that, like I said, the base plates the same thing, okay, and so on and so on. Okay, Anton, question.
Yeah, another question about exam content for steel next week. Is the double connection included? So what I'm saying is, it's based on the last 4 assignments that we did, or
you're gonna design a connection bolted, and then you're gonna redesign it as it was welded, and then you're gonna have a double angle connection.
Okay.
Let me just check. I already did the exam. Hold on a second. I just gotta find it where it is. I just wanted to make sure. Yeah, in other words, it's going to be like very similar to the last 3 assignments, where you did one that was bolted, and then you take the same bolted connection, you redesign it as a welded connection, and then the last one's going to be a double angle connection.
Okay, thank you.
Very similar to what we did in class today. Understand? Okay, I might, I'm going to tell you what size of, I might tell you like what size of angle to use. I might tell you what size of weld to use, so that, I'm forcing you to select something very particular in the table. You understand? But that's about it. But
All right.
Sounds good?
Yes, sir.
I have a question about the vertical bracing.
Yeah, the question about the vertical bracing. Yeah, okay.
The connection for the vertical bracing.
The connection for the vertical bracing. Okay.
I've worked on it, but I'm not quite sure if it's right or wrong, to tell you the truth. Do you mind if I'll show you my?
Yeah. Hold on a second. Let me just stop sharing, and let me just multiple. Okay. Yeah. Share me your screen, because that would be the easiest way.
One moment. I'm just gonna open the file and.
No problem.
Because this it's a bit tricky. I don't know. Right.
Okay, hold on a second. I'm gonna ask so I can also participate. Request remote control. Okay. So
Coming. So this is what I did. I don't know.
well, okay. This is what you did. Okay, number one. Okay, so your VF force is 49.1, right? Okay.
Yeah.
Hold on. Okay, so this is your VF force. Does everybody agree with Nermin? Because I don't remember what the VF force is. Okay.
Yeah.
Okay, Nermin. The other thing you have to start with is what's the size of your column?
It's there. It's 102 by 102 by 3.2.
Perfect. Okay. So therefore, you're using a 3mm weld. Agreed?
Yeah.
Okay.
Yeah.
Now, keep in mind that what you're going to be doing is that I'm going to try to draw the HSS in 3D. Okay. Okay, I'm going to try to draw it in 3D so that you can. Okay. So basically, your plate is going to be going. Your gusset plate is going to be going in here. Okay. So you got to keep in mind that you are going to be welding on one side, two sides, three sides, four sides. Okay. So in other words, if I draw an elevation, here's my HSS. There's my gusset plate going in like this. Okay. And there's my gusset plate going in there. Okay. Fair enough. Now, okay. So now in this case here, okay, in this case here, this is your weld. This is your weld. Okay. This is your force. You understand? You get what I'm saying?
So the L2, yeah. So the L2 should be 4 instead of 2 because like 2 from the top
Two,
and 2 from the bottom.
exactly. Now, if I do the top view here, this is your HSS like this. Okay. There's your gusset plate going in here like this. You understand? So what's going to be
Yeah.
happening is now I'm going to change color. I should have done. Okay. So this is going to be your weld here and your weld here. Okay. Okay, so you're going to have 4 segments, number one. Okay, number one, you're going to have 4 segments. All these segments are going in the same direction of your force. You follow what I'm saying? So,
Yeah. So
okay,
the theta is 0.
I
this,
think theta 2 is equal 0.
exactly, this is 0. So therefore, this becomes a value of 1 here. Okay, theta 2 exactly, Rania, it's 0. Okay, exactly. That's what first thing I want to say. Okay, number one. Number two, okay, number two, if you look at this, okay, if you, unfortunately, the whatchamacallit, the tables don't have 3mm welds, right?
Yeah, I did interpolate. The minimum is 5 millimeter and it's coming to 0.788.
Okay, but what I'm saying is that,
So
okay, so in this case here, you're using a 3mm weld because your wall thickness is 3mm. You can't, it's always, you cannot have a weld that is thicker than what you're welding. Okay, that's number one.
yeah.
Now, number two, you know that VR, okay, if you take the equation, VR is equal to 0.675 W, okay, the area of the weld, okay, AW, XU, in other words, let's, if you want to do it, I have to go get the equation. I don't have the equation off the top of my head, but we can go get the equation, okay? And you just find what the value is for a 3 millimeter weld.
Yeah, this is what I did. I got 0.468.
So you got 0.468 kilonewtons per millimeter, right?
Yeah.
Okay, so that means that if I take 49.1 divided by 0.468 kilonewtons per millimeter times 4 segments, what do you get in
Yeah.
terms of length?
This is what I'm doing right now. 26.2.
How much? 26?
26.2.
Okay, 26.3. I don't care if it's 26.3. I don't care if it's 27, but 26.3, right? So that's what you need. That's what you need in terms to get the resistance. And according to good welding practice, you should not have a weld segment less than 38 millimeters. In other words, 1.5 inches.
Okay.
Okay, so therefore make this 40 millimeters.
Okay.
You see? So that's
Yes.
so that's how you see. So you know, like you need 26.3. Good weld practice says no less than 38 millimeters. Therefore, make it 40. It's ample. Okay. Now, and then, so now you know what the size of your welds are here. Now, if you want to know the size of your plate, well, normally what you would do, okay, like for example, you would take the 102 here, okay. You know you need at least 3 millimeters to put your weld there. You need 3 millimeters to put your weld there. Agreed? So you need 6 millimeters, and then you should have. So what's 102 plus 6? That's 108, right? So if you really want to be cheap, the width of your gusset plate here is going to be 110 millimeters. You understand? That's going to be the width of your gusset plate, 110 millimeters. You understand?
I made it 150.
150. Okay. I don't think you have to go that far. 120 would be ample. You understand? If you
I just like use this, like I have two bolts there.
Yeah, okay. You have 2 bolts here.
Although like one bolt is more than enough because one bolt it's
I know.
giving 79.
Exactly. 1 bolt would be sufficient, but you never have a 1 bolt connection. You have at least 2. So, and now, did you put the 2 bolts side by side like this?
Yes.
Is there a reason why you didn't put the bolts like this?
Not really, because normally we're doing it like that.
I'm just saying, Norman, you understand? So like what I'm saying, like this is all.
Okay, because now I can like have less space for the like the width of the gusset plate. It can be less. Okay.
You understand? So like there's nothing to stop you from putting the bolts this way. You understand? I know what you're saying. Like you did it this way, so you ended up getting like, I don't know. But even if you leave 80 millimeters there, 35 and 35, so that's how you end up getting the 150, right?
Yeah.
Okay, but if you put the bolts like this, you can go narrower, right?
Yeah, absolutely. It can be like
You can go down to
not
120. Like the smallest you can go down to is 110. You understand? The smallest. Because here you have 102, right?
Yeah.
And then you have 3 millimeters there, 3 millimeters there. That brings it to 108, and that just leaves 1 millimeter of space between the weld and the edge of the plate. So the smallest you could go down to is 110.
Okay.
And if you want to go a little bit wider, then go to 120. So 110 would be the smallest, I understand. And if you put your bolts in this direction, it works nicely. Now, when you look at, then if you're looking at, I don't care, this is the top or the bottom, but if you're looking, so here's, for example, the gusset plate that you're going to have at the bottom, right? That you're going to be attaching to. Then if you put your holes in that direction, you put your holes also in that direction for the gusset plate. Do you follow? And then this is going to come here like this, and there's your brace.
Okay.
Does that make sense?
Yeah, of course.
Okay, so you're on the right track, Nermin. So don't like, like I'm just like here, perfect. Like you put everything here. The minimum is this, okay? Perfect. You understand? Blah blah blah. Nice, and I like that. You understand? But I want you to understand that here, for example, the edge distance. Okay, so here, for example, you leave that minimum edge distance there. You make sure you have the minimum edge distance there, and then you can put your bolts in that direction if you want. There's nothing to stop you from putting them in line. You understand?
And for the gusset plate, you said it's gonna be it can be determined by the AutoCAD, or we do have to make it.
Oh, I mean, you mean working out like the geometry of the gusset plate? Yeah, you can do that with the AutoCAD once you got the angles. But then,
Oh.
what you need to determine here, for example, leave an edge distance here of 35, right? Leave here and like let's say you want to leave here 80, okay? Leave that 8. Leave those the same thing. Now, as far as the thickness of the gusset plate, right?
Yeah.
Okay, that's going to be based on what, like for example, what is the here, like you can do the calculation here, see what you need in terms of thickness. You understand? Like, cause like the shearing, the tear out here, if you put them in this direction, you understand? Your AGV here, right, is going to be 135 plus 180 times 2. Do you understand what I'm saying? Because that's a shear there and shear there. And then you can calculate what your T is. Your T is going to be very, very small. You understand?
Yeah.
Your T is going to be very, very small. Okay. So you know that, for example, your thickness is going to be very, very small. Okay. So that's going to determine, okay, so if you have a 3 point something millimeter plate there, right? I mean, I can, you might even be able to go down to a 4 millimeter plate if you want for your gusset plate. You understand? But you'd have to check it to see what's the minimum T you need. And then of course you got to check the bearing here, but the bearing, I mean, these forces are so small, right? So you have to check the bearing and you have to check the shearing, and then you're going to see that your T is going to be very, very small because your forces are not that strong. And then after that, common sense says that, you know, if this is, if I'm using a 3 millimeter plate here, don't forget, you also have to check the bearing. Like once you're going to have to check the bearing for a 3 millimeter plate, right? Now, Nermin, if you want, okay, I mean, there's the equation for bearing, BR is equal to, there's that equation, right? But you can take any thickness. For example, if you take for a 3/4 inch bolt, okay, take the smallest thickness that you have in the bearing tables, okay, and then you can prorate it over whatever thickness you're putting here. You can use that in proportion, okay, instead of having to recalculate everything. Understand? I don't know if I've lost you on that, but
Like it kind of
okay.
I don't know, but I use the plate for it's like 6 millimeter plate thickness.
Okay,
Me, I got 3 millimeter.
you got a 3 millimeter plate.
You might be right, Rania. You're 100%. You could be right.
No, no,
I just like use.
I think a 3 millimeter plate is probably going to be sufficient because these forces are relatively small. You understand? So I think 3 millimeters, because like I said, Rania, when you calculated the T required, what did you get? About 1.2 millimeters, something like that?
Yeah, something
Yeah,
like that.
Exactly. 2
Yeah.
millimeters. You understand? So common sense tells you that, you know, if the wall thickness of
actually,
your
I got the same. I got the same at first, but then I thought there's something is not right because like 2 milli, it's really really small. So I just followed the.
I understand, but don't do that. See, the main difference here, if you can pan up a bit, okay? See, the thing is here is that these forces, you have a VF, it's very small, you understand? So therefore, because of the, you know, like, and that's what gives you some like very low values. Here it is. Here's your VF value. You only have 49.1. You understand? So that's not a big force for, you know, welding and for bolting and so on and so on. So if you use a 3 millimeter plate, it should be sufficient. And if you want to be, you know, ultra conservative, you know, go to 4 millimeters. You know, But I was sure that it's, like I hadn't done the calculations, but I was sure that a 3 millimeter plate would have been sufficient. And because if the bearing here on this plate is sufficient for 3 millimeters, then it would be sufficient for the bearing for on that one. The only thing you have to worry about is the block, the shear block out, and I'm pretty sure that that's going to be sufficient too. So you're on the right track, Nermin. I mean, a few glitches here and there, but you're on the right track. You understand? So this is you understand why this is a little strong now?
Yeah.
Okay.
Yeah, because there are 4 of them,
Yeah,
4 wells.
exactly. No, exactly. So if I would divide this by 2, we would go back to our 26 point whatever. You see? So your answers are correct. You see? And then of course remember that this is 1. It's not. This is 0, and that is 0. Okay. Because this is the direction of the force. This is the well segment that is closest to like it's 0 degrees for theta 2, and it's 0 degrees and 0 degrees for theta 1. So therefore, in this case here, you don't have what we mean by well groups is when the weld segments are in different directions. You understand? Like you have a weld here,
You have
a weld,
only one.
exactly. Here,
Yeah,
all the
we have
welds in
only one weld.
only one direction, and therefore you don't have to worry about. They're all acting in the same direction. Therefore, the MW ends up being equal to 1.0. Okay, because both theta 1 and theta 2 are the same. You understand? But so like here. So that's okay. Good question. I'm glad you brought it up, and I'm pretty sure other people might have the same issues, but you're on the right track. Like there's just little glitches here and there. You understand, Nermin? It's perfect.
One more thing for number 13.
Nermin, I just want to ask you something. I haven't done the calculation in my head, but look at this. 49 divided by 79 should be less than 1.2.
Yeah.
You know what I mean? I haven't done the calculation, but I know mathematically that this, when my denominator is bigger than my numerator, I should have something.
No, I was just doing something. No, you're right. For this one, yeah, I know.
Okay. But then again,
yeah.
Good practice says that the only time you would only have one is when you have that real pin connection. I talked about that. You understand? But if you're using a bolted connection,
I will tell you how I got this 1.2 because like for me, in order to get like this small like symbols while I'm doing the calculations.
Yeah.
So sometimes I just like copy from the.
And guys, like just because it is 2 to 3 times stronger than it actually is, what do you care? You just do what's good according to good practice, and if it's stronger, you sleep better. That's all I can tell you. So don't worry about So anyways, just change this number in your calculations.
Yeah, of course. Yeah, no, this is not the final. Don't worry. You will not receive it this way. Don't worry.
No, I'm not worried about it. I'm not worried about it. Okay, I'm just pointing out something that I just caught the corner of my eye when I saw that you're, Okay, sounds good. You're on the right track.
Okay. One more thing for number 13. Again, it's gonna be like because we are gonna design for the columns, or I'm not quite sure. We will be designing the double angle connection for the Gerber girder and the perimeter beams.
Yes.
So,
like the Gerber girder is gonna have. Okay, so what's your question? Go ahead.
This is in relation to the columns, right?
Well, first of all, okay. So let's stop sharing, and this way we can. Okay, so first of all, let me just get the whiteboard. Okay, so we're all on the same page. Okay, when it comes to this. Okay, so first of all, let's talk about. Here is the Gerber girder. Here's the exterior column. Fair enough?
Yeah.
You agree?
Yeah.
Okay, so what's the first thing I need to know?
The size of both.
If you look at the examples we did in class, what's the first thing we establish?
I'm not sure what's here. It's like
the width of the beam,
Sorry?
W of beam,
Well,
the thickness of the beam.
no, even before we do that, even before we worry about the
like the
thickness of the,
bolt, like
even if,
the type of bolt.
what's the first thing we need to establish in terms of designing something?
Geometry. Size.
Okay, in other words, we need to know the force. We have our geometry. Here's our geometry. We have no choice. We said that this is going to be the size of our column, and this is going to be the size of our beam. We have size. We have geometry. What's the first thing we need to determine?
The force that it could withstand.
force.
Exactly. So in other words, we have to go and determine what the VF force is. Where do we go? Where do we get the VF force?
The W shapes. No.
Why? Why? You did the whole analysis.
Oh yeah,
How
you're right. On 88. Well, okay, yeah. That's another.
you can't even use the beam load table because this has a cantilever, so it's not simply supported.
Okay, you're right.
So you're not even allowed using the tables in this case. Understand? So where do you go get your VF force?
ADA.
ADA. So you go to your envelope in ADA and you go look at the maximum shear force in ADA, and I think it's in the order of about 270 something. Can anybody go and find the value? So we'll all have that value, but you should be able to go find that VF value in ADA. Or hold on a second. Let me see if I can. I'll stop sharing this, and I'm not sure if I. Hold on a second. Yes.
The maximum was 320, I think.
I don't know. Like I'm gonna go look at my ADA and we'll look at your ADA. How's that? Okay, let me.
320.9.
How
That's
much?
the left. 320.9 for the left cantilever girder.
320.9. Okay. Well, that's not what I get. I'm sorry to say, but that's not what I get. You sure you got 320.9?
Well, this is we're looking at the shear envelope right now.
Okay, and the maximum shear you have is?
Let me just check here. Yeah, on my file it's 320.9, the biggest one.
Can you share your file with me?
Sure.
Is it 318.12?
Yeah, sure. I got 318 as well.
Okay, show me your ADA. Show me your ADA. Who's telling me it's 318?
I do.
No, but does somebody have their ADA open that I can take a look at it and share it with us?
I have it on the file itself. Like I have a screenshot on the file. I'm gonna share again so I can show it to you. It's there. And don't worry about this. What's the record there? This is the.
So I don't see 318.
Isn't this?
Is that where the connection is?
No.
Okay, so
this is the connection of the girder. Okay.
Is it 424? It's like if we look at the graph.
Where's 424?
Like if never mind.
No, this is the moment. This is the bending moment. Oh my.
This is where you're connecting.
Yeah.
This is where you're connecting. So which is the higher one?
Okay.
Sorry?
Is it 203?
Is it? You tell me. You know, here you are. Are you asking me or you're telling me?
No, I'm telling.
Isn't this where you're connecting? So shouldn't this be your shear force? You're not connecting here. You're not connecting anywhere else. You're just connecting right there. So ADA tells you that your shear force is 203.9 kilonewtons. Now let me stop sharing, and I want to see what I have in terms of my. I'm going to show you my ADA. Okay, so let me show you my ADA. Hold on a second. Share screen. I'm going to go to my ADA here, share. Yeah, see, I have 203.9, the same as you, Nerman. So that's my VF force.
At least I got something right.
No, but you understand? You had it right, but you didn't even know what you were designing for. You understand? Because guys, what you have to visualize, okay, what you have to visualize is, of course, is hold on a second. You know, like, so here's my column here. I mean, I put a support here, but this is my column here. Okay, this here is where my other column is here. And even when I design my drop-in beam, okay, my drop-in beam, for example, that connection that we designed together for the drop-in beam, this is where I came to get the force for the drop-in beam, for the connection right there, because that's where the beam is being connected to the overhang. And that's why I had a VF force of 96.4. You understand? I didn't take 86, I took 96.4, and then, you understand? And I looked on the other side to make sure that I would also not exceed that value. So I go look on ADA where I'm going to repeat that connection for the drop-in beam, and I go look for the highest force. Oh, 96.4. I mean 96.37. I call it 96.4. And then here I look at on this side 88. No, definitely not here. Okay. In other words, what this is, okay, is that crushing. If I was to calculate if I would need, this tells me whether or not, okay, like for example, the reaction here would tell me if I would need, for example, stiffeners in there, like we did that already. So this is what I want. So right now I know that the shear force that I'm designing for is 203.9. We all agree with that? Okay, so now we'll go. So now, share screen, go back to the whiteboard. Share, okay, clear drawing. Okay, so here we have, so I have my VF is 203.9 kilonewtons. Now we said we're going to be bolting to the beam, and okay, so we go to the table. I don't have the table, but if we go to the table, we would look for, we know that our beam size is 610. Keep that in mind. That's our Gerber girder. So make sure you take something that, you know, that it can actually fit in. And we know that we are going to be having bolted to the beam. So I don't know, for example, what the VR values are. Now, are you, like, to be conservative, I'm going to take the VR values where the threads are going to be intercepted. So let me just go, let me see if I can open up the table. I can see if I can find a table. Desktop, let me see if I can find a table, Dawson, so that we can look at this together, put you guys on the right track. Courses, steel structures. Now, where do we do the double angle connections? I'm looking for my file where I can probably find a table. I think well, hold on a second. I'm almost there. Double angle connections. I think I might be able to open it. Oh, there we go. So I'm going to share this. Hold on a sec. Do you guys see the table in front of you, or do I have to go and open the share? Is it shared with you or not?
No, it's not. Just share your board.
So what do you guys see, Rocky? I'm going to stop sharing. I'm going to go share, and I'm going to make sure I pull up the table. Oh, there we go. So everybody see the table now?
Yes, sir.
Okay, so there we go. So here we go. So now, guys, the same thing we did in the example. All we need to do is, of course, where are those lines? Okay. So basically, we know we're going to be using 3/4 inch bolts. Okay, and we know that we are going to have our beam fall, and we need to have what's the size of our VF? 2 something. Okay. Now, okay, so if you look at this, this would be sufficient, right? We all agree? We all agree that that would be sufficient?
Yes.
But what's the problem?
The size of the beam is
exactly. So therefore, what you would do, you automatically go to here, okay? So you don't care if you have a VR of 634. Okay, you know that your beam size should fit in between there. Okay, and therefore you're going to be using 4 bolts. Okay, and then you continue. Okay, minimum size of web thickness, and that's where you check the minimum size of web thickness, blah, blah, blah. Okay, and of course you can prorate that 270 over that to get what that is, which would be very small, so you know your web would be okay. And then once you did that, you come to this side of the table, right? Because this is where you would be, right? And you know that you are welding to the, now this is where I was telling you this morning, okay, is that you have to look at your column size. I don't remember what the size of the column we designed, because I don't remember what it is. It's a
200 by 27.
400 by 27? Can't be. We didn't.
No, 200 by 27. This
Okay,
is the series column.
okay, 200 by 27. Therefore, I would have to look at my B here to see what I need to do in terms of being able to put 2 angles welded to that flange. So that B is going to give me a restriction. Okay. So most likely, so now here, for example, I know that if I use this size of angle, okay, and I only use a 5 millimeter weld, I get 436, right? And you look at here, that's whether it's 89, whether it's 76, I end up with 436, right? So that means that if all of a sudden I need to cut my angles, down to, let's say, so can anybody give me the B? Give me the B of the column for a 200 by 27. Does anybody have that table in front of them? Nobody has that value. Okay, so you're gonna have to do it on your own.
It's 133.
133 millimeters. Okay.
Yeah.
So now you know that, for example, and what's the size of the web for a W200 by, what was it? A W200 by, what was the beam that we had there? Is it W610? What's the Gerber size that we have? 610 by, it's not 92, it's the other one.
It is 92.
It's 610 by 92. That's what we okay.
Yeah.
So, and what's the web thickness for a 610 by 92?
Moment.
Does anybody have that information?
Just one second.
Sir, is it 10.9? Because I'm looking at mine, it says 10.9.
Okay, I don't know. Like you're telling me it's 10.9, so it's 11 millimeters, right? So that means that these angles here, like this, okay, these angles here, like this, okay, you will leave 13 millimeters there, okay. Now, if I take, Nermin said this was 133 minus 13, right? Minus 13, that leaves me 110. Divided by 2, how much is that? 55?
55.
Okay. So therefore, I would be using a 55, and then we need to leave the size of the weld, right? In other words, we need to provide at least 5 millimeters on each side. So in other words, minus 10.
So it's 45.
45, okay? So now, if we look at the double angles, is there anything that an unequal leg of 78 by something? I'm not sure. You understand? So let's go look at some double angles and see what we have. If not, we're just going to ask them to cut it. You understand? If we can't find a standard size. So the maximum leg size is 45, right?
Mhm.
So so I don't know where we can get the double angles. Where's the double angles? Double angles. Does anybody have the table for the double angles to see what the size of the angles are that are available?
I'm looking right now, sir.
Sorry?
I'm looking right now.
I appreciate it if you, because I have to go open my table. I have to go find one in my lectures and open my table. This is the advantage of having a steel book. It's like you just flip back. Yes.
Yeah, it's actually supposed to be 55 because like 133 minus 13, it's 120.
Oh, 120. Okay. We have, sorry, that's 120 divided by 2. That's 60 minus 10. That means 50. Okay. So the maximum, so that means the maximum space that we have here to go to the edge of the column. Okay. And then even at that, I wouldn't go right to the edge of the column because you have the fillet of the column that you have to worry about. You understand? I wouldn't weld right there either. I would give myself some room. So the very maximum space I have is 50. So what's the smallest, what size angles do we have?
So I have a question.
Well, let's finish this first.
No,
okay?
It's about this, I think,
Okay.
because you chose 13 as the thickness.
No, that's the spacing. In other words, we said that the web was 10.9 millimeters.
Yeah, exactly.
I need to leave 2 millimeters space so that they can drop it in. That's the tolerance for erection. So I have 13 there. I have 5 millimeter welds on this side. So this all takes away from what I have in terms of width, right? So I have, and then I have a maximum width here of 133. So 133, take away 13, take away 10, and this, and I would even take more than 10 because I wouldn't want to, like, if this is my column here, I don't think I would want to weld right there where the fillet is, but you know, that's going to be another problem. But so in other words, 133 minus, so we said this is 120 minus 10, which is, I'm sorry, 120 minus 10 gives me 110. That gives me 55 divide in a sense. So like what are the size of angles that are available?
The smallest 76 is by 51.
So 76 by 51. Great, Nermin. Okay, so look. So in other words, 51 times 2 is what? 102, right?
Yeah.
Plus 13 plus 10. How much does that give us? 125, right? And you said that we have 133. So that would give us enough room to place our welds on each side. So the angles that you're going to be using is a 76 by 51. And then by what thickness do you want to use? Well, then you have to go back to the table and check it here. You understand? You have to go back here and check according to this.
But don't we have a weld of 5? So.
I'm sorry?
Or, sorry, that's nothing.
No, what I'm saying.
We have a weld of 5, right? So we can take the 6.4 because like the lower thickness is gonna be 4.8.
Yeah, and then you just have to, like, I'm pretty sure here they say that the minimum web thickness is 7.7, right? We agree?
Where are you pointing, sorry?
Oh, okay, hold on.
Yeah, it's in the bottom left.
Right here. That's for the web thickness. We know we're okay, right? Because we have, what do we have? We have 10.3, so that we don't have to worry about. We agree, right? Minimum required thickness of framing angle, 6.9. We agree?
Okay, I thought that you're talking about the weld. I don't know.
6.9, right? We agree. The minimum.
So we have the 7.9.
What do you mean? Hold on a second. But I want to be checking here first. I have 6.9, but that's for a force of 632, right? But we don't have 632. What do we have?
203.
So 203 divided by 632 times this thickness, we're way below this, right? So that's okay. Now we want to go here, right? Minimum thickness material with frame on one side. So in other words, we have to check to make sure that the web thickness of our column is at least 3.8, and I think we have that for our column. I'm pretty sure that the thickness of the flange is at least 3.8. We agree? Do we agree?
Yeah.
Yeah.
Okay, and then the last thing we have to check is if we have a 5 millimeter weld divided by 0.75, we need a minimum thickness of 6.6 to provide that weld. And you're suggesting 6.4, right, Norman?
Yeah. So
Well,
we can go to the 7.9.
I would go to the 7.9 to make sure that, you understand?
Okay.
Because in other words, if you remember, if we're using a 5mm weld here, okay, 5 divided by 0.75, that should be the thickness of the leg, and therefore 5 divided by 0.75, that gives me 6.7. You can use a 6.4mm weld. That's just, you understand, it's close enough, Norman. So the angle would be a 76 by 52 by 6.4. How's that? With a 5mm weld, understand? And it should all fit on your column. And of course, you're going to have 4 bolts in there. That's the design.
Okay.
Easy enough?
For the, yes, of course. And okay, and also for number 13, we need to design for the HSS for the interior columns, right?
I'm sorry, I didn't hear
Or
that.
not really. For the number 13, we need also to design for the interior columns, or we don't have to.
Your question is very vague. I don't understand it. What do you mean? The interior columns?
Yes.
What
For
about
the
the?
connection for the interior column with the Gerber girder, with the.
There's no connections. I mean, all the interior columns, the beams go right over the columns like this. So what do you need to connect? All you want to do is you want to make sure you put some kind of bolts here so that it's all fastened together. But you understand, like this is your beam. It's going right over the column. So how is the force being transferred to the column from one member to the other? It's not going through any of the connections. The connection here is just so that during erection, everything's going to stay in place. You understand? So if anything,
okay. So we just like erect the columns there, and we don't connect it to the Gerber girder just because it's in compression.
You'll connect it, like you'll put 4 bolts here, but these bolts are just so that during erection, the thing's going to stay together, but there's no force in there. You understand? What I'm saying is that there's nothing to design. Everything, the connection here is more for erection purposes than actual design. You understand? So for example, this is my beam here. Like I told you to make the cap plate here the same width as your base plate. Okay, your column sits here like this, and this is the bottom flange, and therefore you're gonna have a bolt there, and on the other you're gonna have 4 bolts, but you don't have to design it. It's just for erection purposes. Saying because the force is going through the member into the column, so it's not going through any transfer mechanism like you did for a double angle. You understand? Because everything is going right through the member. It's not going through anything that has to transfer that load. Like for example, in a double angle connection, well, it goes from the beam into the connection, into the supporting member. So then you have to make sure everything's designed properly. But here the force is going right from the beam into the column. So there's nothing to design there, you understand? So all you're going to do is you're going to provide 4 bolts here so that when it gets erected, they stay together, you understand?
Yeah.
Okay, so there's nothing to do for the interior columns except to provide 4 bolts, you understand? So that should clarify that one. Okay, that's good. I'm glad we're having these questions because it kind of clarifies things for you guys. So that's good. Any more questions?
Sir, I have a question.
Go ahead, Anton.
About I just don't understand how we got 52 and previously, the design is a 76 by 52. I just don't understand how we got the 52.
Well, what we did was we, hold on a second. Okay, clear all drawing. Okay, so we start with our geometric constraint. These are the edges of the column. Okay?
Okay.
That's the edge of the column. Nermin told me that, and you should check this, Anton. Nermin told me that
Yeah, the full width is 133.
the B of the column, she told me it was 133 millimeters.
Check right now. For 610 by 92.
No, the column. What are you talking about?
Oh, sorry. HSS. Okay.
You know, we're talking about the column now. And she told me the column we had designed it to be a W 200 by 27, I believe. Is that what you said, Nermin?
Yes, sir.
W 200 by 27. So you take a W 200 by 27, and since you're going to check the width of the column, also check the thickness of the flange, just so that we can make sure that everything's okay. And give me also the thickness of the flange.
7. That's one.
Is it 133? That's all I want to make sure of.
I'm looking on my Excel file. Yeah. Okay. Yeah. The B is 133. Yeah.
So B is 130, and what's the value of T? Because we didn't check that. We just
T
assumed
is 8.4.
8.4, and if you remember what we did, we need a minimum thickness of the supporting, which was less than 8.4, so we're okay for the supporting member, right? Now,
Yeah.
here what we're doing is we're starting off with other geometric requirements, okay? So we're starting off with, okay, I have to leave a space between the two angles.
Okay, yeah, that I understand. Okay.
So we said that we had 10 point something, 11, we said we're gonna leave 13 millimeters here, okay?
Okay.
We're providing a 5 millimeter weld here. So if I'm providing, I need to have at least 5 millimeters in order to put a 5 millimeter weld there.
Yeah,
You
okay.
understand? And I need 5 here.
Same thing, I guess. Okay, yeah.
Okay. So if I take my 133,
subtract 13, 5 and 5.
Minus 13 gives me 120. Minus 10 gives me 110. And they're divided by 2 gives me 55 millimeters. So if I use a 52 millimeter leg here, I'm going to have enough space to put my weld and make sure I'm not right at the edge. So that's how we end up with us, because where you're going to be bolting, it's going to be 76 millimeters. Where you're going to be welding, it's going to be 52 millimeters. And we said that the thickness was going to be 6.4. And that's how we ended up getting that.
Okay. And the 6.4 is because it's listed in the...
Well, because we said, like, if you're putting a 5 millimeter weld and the good practice requires that you shouldn't go more than 3/4 of that.
Oh, okay, I understand. Okay,
we ended up getting with 6.6, and we said we're not gonna be fretting for 0.3 millimeters, just to understand.
Yeah, I understand. Yeah.
And especially if you consider what we actually got in terms of resistance, what we actually need, I won't worry about that.
Yeah, so the 6.4 is when we did the 5 divided by 0.75, it gives 6.7, and then we don't count the 0.3.
Yeah, I wouldn't worry about 0.3 millimeters.
Okay.
My hair is thicker than that.
Okay, I understand. Now I get it. Thanks, sir.
Okay, so that clear now?
Yes, sir.
Okay, good. And so there, now we've designed the one, and now, you know, the other two are going to be, the force are so light, guys, that you're going to end up with maybe 2 bolts, and, you know, so don't worry about it. Like, so the other 2 beams are like the perimeter beams, even on the long side, on the short side. The only thing you have to worry about is that like you are literally, you know, placing your connection in between the flanges of your columns. So keep in mind that when you're looking at a wide flange, okay, keep in mind that, okay, when you go to the table, get the value of here, like where the field, because you want to have your connection stay on the flat part. You don't want to put your angle on this part of the beam. So that would be the maximum width that you can work with when you're putting your connection inside the column. And that you get that from the tables. If I hold on a second, I don't have any. No, I don't have any. I'm gonna have to. So keep that in mind, that when you're looking at this, this is D. I think this is called. They even give. I think the big capital T in the table is what this distance is, and that's the distance where you no longer have the fillet of the inside, and that's what you have in terms of available space to put your connection in. Okay, so if you're welding in here, even if you're welding, you want to make sure that the leg of the thing here stays on the flat part and doesn't encroach on that fillet. That's the only thing you have to keep in mind, and that's it. So, okay. Any more questions? I love these questions, guys. Good.
I have a question, but it's for the wood project.
Good. I'll answer any questions at any time, Rena.
Okay. So I'm just like I'm on the step where I'm doing my columns.
Okay.
And I just have like a problem with the column that's near the stairs. It's not, when I do the equation PF over PR plus MF over MR and so on, it doesn't give me less than 1. And like, even if I change the plies,
Okay, but
still,
are you're talking about which columns now? Can you just hold on?
I'll share my screen.
Yes, share your screen because this way I can see what you're talking about.
Can you see it?
Yeah, but I want to know, like, for example, which columns are you talking about?
I'll show you. Okay, so there were these columns here, right? So the column that goes in L2 and L2 here, everything else works with the ones I chose, but not the one that's on the stair here.
Okay, but here, let me just, I want to show you something, okay? So that we're all on the same page. Okay, so this is not a column, number one. Okay, the column is here.
Okay, yeah.
And the column is here, and the column is here, okay? Now, whatever works for here will definitely work for here and for here.
Okay.
Okay, that's because here the tributary width is smaller than the tributary width. So whatever column you got it here, you can repeat it there, and you can repeat it there, not a problem, okay? And here, okay, when you're calculating the PR, okay, when you're calculating the PR for you're using a 3-ply.
No, I use your sheet for the column, and it 2-ply seem okay.
You use a 2-ply for this column here.
Yeah.
And it turned out to be okay.
No, that's the one that's giving me problem actually.
Okay, well, that's what I'm saying. So like I gave you that Excel spreadsheet, right?
Mm-hmm, yeah.
Okay, in that Excel spreadsheet, if you put LD equal to 2,200, okay, and you put LB equal to 300, what do you get for the PR value?
I'll just scroll down, okay, because I have it here.
Okay, what do you get for the PR value?
There, 59.5.
Okay, so that's your PR value, right?
Yeah.
And so what did you get for, so in other words, and this is what you're using the interaction equation, and it's still not working?
Yeah. Mm-hmm.
What do you get for MF? Because maybe your MF value is completely off.
It's on my trial for the case 4 that I'm having this trouble. So like my MF is here 2.1.
2.1 kilonewtons. Let me just check something. If I'm not mistaken, I believe that the WF, the wind load was about 1.1 kPa. Is that it? What was the?
I got 0.94 kPa.
4.84 kPa for your wind
load? 0. Are you talking about like the companion load, or are you talking just the wind load?
Just the wind load.
Okay, 0.94 kPa.
0.94 kPa multiplied by 1.4. Okay, so 0.94 times 1.4 gives me 1.32 kPa times. What was the length of L2 I told you to use? Or the span of L2? What did I tell you to use?
Let me check.
L2. I gave you that. 2.13, right?
Yeah.
So 2.8 kilonewtons per meter, WL squared over 8. So you got an MF of how much? For load case number 4, what did you get your
Yeah,
MF?
I'm getting there. So 2.1.
I think it's slightly overestimated. 2.1.
I think it's 1.68, right?
Because what I just did, Rena, is you said that your wind load. Okay, look at this. You said your wind load was 0.94 kPa, right?
Yes.
I multiply that by 1.4 on my calculator, so 0.94 times 1.4. That gives me a factor load of 1.32 kPa.
Yeah.
Okay. Now multiply that by my tributary width, which would be equivalent to. You said that the L1 I told you was how long?
2.13. Not L2, 2.13.
2.13 meters. So I multiply that by times 2.13. So I get a WF equal to 2.8 kilonewtons per meter. Okay.
Okay, yeah, that's what I get. Yeah.
Okay, then I take an L of 2.2. Okay. So W times L squared over 8. So therefore I take 2.8 times 2.2 squared divided by 8. I get an MF of 1.7.
Okay, because I'm doing L 2.44.
Okay. So you're doing those. Okay, but even at that, what did you get for the MR for a 3-ply SPF?
I did a 2-ply.
Pardon?
I did a 2-ply.
Oh, it doesn't work for 2-ply, right?
Yeah. No, I haven't done that because I was stuck there. I was like, oh, what am I doing wrong?
Okay, so I don't think a 2-ply will work there. You understand?
Okay.
And if you don't take advantage of my tables, okay, for the PR value, if you stick to the PR values if you don't take advantage of my Express sheet, all your columns are going to end up being 3-plies.
Okay. No. I did take your table for this one, so this one is the only one that I will change actually. Then for the 3-ply, right? Because this one is
exactly. Like if you use a PR that you get from my table, because in reality, the B will be laterally supported, so therefore you can actually recalculate the PR value in the tables. You understand? If you don't do that, all your columns will end up being 3-plies because the PR values are very, very weak because the B is the one that governs. You understand? And you'll end up with 3-plies for all of them. But you should be able to go down to 2-plies for the smaller lintels. You understand?
Okay. So, but the L is 2.2 or 2.44 then?
Well, it's like 2.44 is the total height of your wall. Okay.
Okay.
So 2.44 is the length of the wall at 8 feet. Okay. But then if you take away the height of the lintel,
okay, yeah,
you can go down to 2.2. You understand? If you want to, but leave it at 2.44. It's more conservative, Rena. Okay. Don't worry about that. All I'm saying is that is a good value. That's without breaking your head. And if everything works at 2.4, it will definitely work at 2.2. You understand?
Yeah.
That's all I'm saying. So it's a good starting point. And then, like you said, if you start getting like very close to 1 and you want to fine tune your calculations, you can go back and refine the lengths. You understand? But
no, yeah. If you see here, I have like all the values for case 4, and everything's fine, but except the L2 column.
Yeah,
that
that one's no good. So, like I said, I like the way you're doing it. Nice, very nice.
I copied all your Excel.
Don't worry about that. That's why I want to give. That's
no,
why.
Like I've been learning a lot with Excel, with the things you do on Excel. It's very nice how you do it.
Okay, well, I'm glad you appreciate it. So that's good. Well, no, you're on the right track. Like I said, I was almost sure that for that one lintel, for that one built up column, I was sure it was going to be a 3-ply. You understand? And now that I gave you the correct values of PR for those built up columns, based on the fact that you can laterally support the B and recalculate the PR value based on an LB of 0.3 meters, because the guy will nail at every foot. You understand? The sheeting to the column, and that's going to be providing the lateral support, and therefore you can recalculate your PR value based on it. Because as I was saying, hold on a second. Like those tables are built up columns like this, okay, and they're assuming that the unsupported length is the same whether it's the B dimension or the D dimension. You understand?
Yeah.
So, and therefore what they're doing is the B is always the one that governs, you understand? And on top of that, because it's the PR equation for built up columns uses 0.6, this already, reduces the B significantly than the D, you understand? Times, phi FC A, you understand? This is another thing that affects the resistance. And therefore I said, well, if we nail the column, then we can recalculate this based on an LB of 0.3 meters. And that's what the Excel sheet does. It checks to make sure that it's still the one that governs, because it calculates both the PR on the D and the B at the same time. But at least you get the real PR value because of the way it's going to actually. And then on top of that, if you look at, you understand, when you're making a window, your B is in this direction, right? You always have some kind of blocking here to make the actual window size. So your column is never the full length of your wall, you understand?
Yeah.
So there's always some kind of lateral support. And I know that in my case, when I put the plywood sheeting in here, you understand? Okay. So for example, here, if it, like for this column here, I would use an LB, the height of the window, you understand?
Okay, yeah.
That's what I would use as the LB value, the height of the window. For all the walls, I can use an LB of 0.3 because I know the sheeting is going to be nailed at every foot. But for this column here, I would use an LB, the height of the window. Understand? If I was doing this to double check to make sure. Because here the sheeting does not go across. You understand? It only goes to the height of the window. So. And if I was doing this for a real project, this is the value I would put in my spreadsheet to see what the PR value is for that built up column. LB equal to the height of the window and LB equal to 2.2 meters, or you can put 2.4 meters if you want. You understand?
Okay, yeah.
You're on the right track. Very nice. Very nice. So
great, thank you.
So you guys are doing great work. Great. Sounds good. Oh, okay. Any more questions? I guess we can pause the recording.